All right, here we go. Percy on demand. Now check it out. Here's the situation. I can't believe a lot of you have come up to me, Mr. Percy, I need the stoichiometry calculations. This isn't going to be tested for a couple weeks, but I guess you've worked so hard and are so far ahead, and we're learning this stuff so well that you're ready to get started on this, and that's fine. I think I'm going to make another video next week. But I think, given the high demand for this, oh, no pun intended, or pun intended, on demand, that I will do a couple problems out of the packet here to kind of get yourself familiar with how this works, okay? Again, this will be a little fast, but I think this will help for you overachievers that want to get a head start on this, okay? What I'll try to do next week is make a more in-depth video that goes a little slower and talks a little bit more about the why, the how, and everything else, okay? Because this is the first time we've done this here in this building. So, again, it's at the end of the year, but this is a skill we want you to leave with. I know the high school, they'll go much more in depth on why this happens, how this happens. But I think if you're familiar with this, this is a good skill to take with you, okay? And it's a very doable calculation. So you need to open up your packet to page 79, and this is under the extra enrichment. Guess what? It's not, it's required. And let's take a look at number 1. We have the equation. 2, it's already balanced. That's important. NaOH, sodium hydroxide, plus sulfuric acid, H2SO4, yielding in the products 2H2O plus Na2SO4. Ask yourself, what's Na2SO4? High sulfate, high sodium M&M. Remember, metal, non-metal, ionic compound. Sodium sulfate, high water. Hello, who's this? What's this? Oh, sulfate. Oh, sulfuric acid. Remember we had the acid naming nomenclature rules. Yes. And look at this, sodium. Oh no, it's hydroxide, NaOH. Remember the EOA, again, metal, non-metal, ionic. Acid, hydrogen at the beginning. Non-metal, non-metal. Water, non-metal, non-metal. Covalent compound, polar. Metal, non-metal. Okay? Sodium, Na plus, SO4, 2 minus, Na2SO4. Okay. So how many grams of sodium sulfate? So we need to figure out how many grams. This is actually like lab. In a lab situation, if you make this material, you can predict how much material you'll end up with, how much will react. Okay, this is pretty neat. Will be formed, how many grams of sodium sulfate will be formed if you start with 200 grams of sodium hydroxide and you have an excess of sulfuric acid. Don't worry about the excess part, okay? Don't worry about that. They'll get to that in high school. Again, it's not an issue here. They'll get into something called the limiting reagent. Okay, we'll probably do that in probably next year, but we'll just get the basics down for now. So we need to figure this out. So as we always start these problems, you write down your given. And the balanced equation is very important. You'll see why. So I'm starting off with this amount. Okay? I have 1 mole of this. 1 mole of this, we take the molar mass. That's 1 mole of this. I have 2 moles of this. And so on and so forth. Now check it out. Start off here. 200 grams of NaOH. Back to dimensional analysis. Here we go. What unit do I need down here? Grams of NaOH. Well, what do we know? Oh, the molar mass. You find the molar mass. The molar mass, it's a pain in, never mind. Okay, so the molar mass is 39.997 grams per mole of sodium hydroxide. So what's the equivalency here? We need to convert to moles. This is 1 mole of NaOH. So 1 mole of NaOH is that. This looks like a mole calculation. Okay, but here's the situation. We've pretty much worked with this half of the equation, the reactants. Now we've got a transition. Okay? We've got a transition, and using the equation, we see we have 2 moles of sodium hydroxide. And we're working toward sodium sulfate, where we have 1 mole. So here's your first part. Part 1, right here, convert to moles. Part 2, work with a mole ratio. Right? So what will we put down here? Moles NaOH. Well, how many moles do I actually have? 2. Okay, now we're transitioning from reactants to products. Now let's look ahead. We got to work with sodium sulfate. How many moles of sodium sulfate are present? Look at this relationship. 2 moles here with the coefficient, 1 mole sodium sulfate. Okay, look where we're at right now. All right? So now, if we look here, cancel, 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 cancel. But guess what? It wants grams of sodium sulfate. I have moles. That's easy. Easy mole calculation. So right at the bottom, to get to grams, I've got to get rid of moles. So I write over here, 1 mole of Na2SO4. Bye-bye. Peace out. See you later. What are we left with? We need a mass. So hold on. We need grams of Na2SO4. What mass? Huh? Oh, the molar mass. You find the molar mass. The molar mass. It's a, never mind. Pain in the mass. Okay, so sodium sulfate is 142.04 grams of sodium sulfate. And assuming I know how to pop numbers in a calculator, you would take 200 times this, divided by this. Your answer should be approximately 355 grams of sodium sulfate you would find that would have reacted. So if you start with this and you have excess sulfuric acid, when these react, you have a certain amount of water, and you also would wind up with approximately 355 grams of sodium sulfate, okay? That's how you do it. It's very simple. It's almost like you start on one side, reactants, transition with the mole ratio from one to the next using the actual coefficients. If this was a 1 NaOH, you put a 1 there. And then you work the other side. In this case, it's the products, and you get your answer. All right, that's the first one. All right, leave it up there for a second. Y'all can see it. Again, I'm doing the best I can. I have 5 minutes left, but I hope this will get you going for the weekend. All right, I'm going to erase it. Here we go. Let's take a look at another one. Page 79. Let's go with PB. I've had too many peanut butter and lead sandwiches today, I think. I'm going crazy. I'm going crazy. It's all about being crazy. Here we go. 4. Ooh, 4. Coefficient 4. LiNO3. You should be saying what these names are to yourself right now. PB and lead sandwiches again. PbNO3, 4. Oh, what Roman numeral would you have here? Because again, you've got PbNO3 negative, or plus. This will be lead 4 nitrate. Plus, what do I have here? Lithium sulfate, 2Li2SO4. Okay. So, let's take a look at what we have here. What are they asking us for? How many grams of lithium nitrate will be needed? Oh, we got to know how much to add. Oh, a chemist does these calculations. To make 250 grams of this. This is the other way. This is too hard. How dare we go the reverse direction? It's not hard. Okay, so let's write down what you have. You need to put a little parenthesis here. How many grams of this do we need? Then we need to take a look at how many grams, okay. We need to make 250 grams of lithium sulfate, so we're going to go backwards. So here's your mass right here. Here's your 250 grams of lithium sulfate. You have enough lead 4 sulfate to do the reaction. Whoa. Yeah, we're over here, yes. Enough lead 4 sulfate to do the reaction over here. So we need to find out, this will be in excess. How much of this do we need to add to an excessive amount of this to get that exact amount of lithium sulfate? Okay? So we need to do a calculation. So we write down here, so start over here. Bring it over. 250 grams of Li2SO4, lithium sulfate. Okay? And again, Mr. Parsi has 2 ugly sulfurs in his basement. If you knew your stuff, Li is a +1, it's an alkali metal, straight cray-cray. SO4, 2 minus, to become neutral, Li2SO4. Remember how we counted the number of lithiums to balance it out. Here we go. What value do I want down here to move on? Grams of Li2SO4. How many grams do we have? The molar mass. The molar mass should be 109.94 grams of lithium sulfate. That's equivalent to just 1 mole of Li2SO4. And now, cross it out, peace out, see you later. Now, we've been working from here, we need to go back. We're starting to think about transitioning. We have our data, we have our, our information to go from one side to the other. Now to really go from one side to the other, we need to analyze what we actually have. We have 2 moles of lithium sulfate. So now to transition, our mole ratio is going to be this. I need moles here. How many moles do we actually have? 2. 2 moles Li2SO4. What do we need to see? We're working to see how much lithium nitrate is needed. So now we write down 4 moles of lithium nitrate. No, 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 you're grounded to nitrate. How many times did I say it? 3. Is that a positive or negative thing? Negative. Lithium plus 1. Oh, the old school stuff we used to do. Okay. So now we've transitioned over to here. Now we're getting close to figure out the actual mass we need to add. So cancel, cancel. Now we need to cancel this unit because I need grams of LiNO3 here. So you've got mole calculation, mole ratio to transfer from one side to the other, and now another mole calculation. Ooh, 2 mole calculations with a mole ratio. Real hard, guys. Okay. Now, moles goes down here. I don't know anything else. I've already accounted for my coefficients up here. So to get a molar mass, it's always 1 mole of the substance. So we're going to go 1 mole of LiNO3, and the molar mass of lithium nitrate, 68.946 grams of lithium nitrate. Cancel out, cancel out. After doing this times that, divided by this times this, our final answer should be approximately 313.56 grams of lithium nitrate. So I would need, if I have an excessive amount of PbSO4, now where's that excess, what's going to happen to that excess amount? It just won't react. It'll just sit in the beaker, okay? That's what we're talking about, that excess that we have. Not all of it will react, okay? So if I have this as a product, this is how much I'm going to need with an excessive amount of lead sulfate, okay? So there's your answer for that. Again, mole calculation, transition, mole ratio, go real time with the coefficients. If there's no coefficient, it's a 1. Then mole calculation again to get the mass, okay? And I'll do one more on page 80. It's a pretty easy one. All right, you have the answer. One more. I can't believe I'm able to do this. The bell's going to ring, but hold on. I'll wait 1 second. Here we go. We've got magnesium, number 3 on 80. Magnesium plus 2 sodium fluoride. Again, why don't we have Mg2? Say it to yourself. Say it. Why don't we have Mg2? You know why. You know why. What do you want to say? I will. It's a metal. Gee, he wants to lose 2. Oh, so another magnesium is going to come in and give it 2. No. You know why. It's not a Dr. Brinkelhoff. Don't forget Dr. Brinkelhoff. B-R-I-N-C-L-H-O-F, parentheses 2, because remember it's diatomic. Okay, here we go. Sodium fluoride. Where am I at? Yields. MgF. 2 plus 2Na. Na 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 na. Na 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 na. Hey, hey, hey. Goodbye, sodium. How come that's not diatomic? Sodium wants to lose 1. It's an alkali metal. Straight craziness. So is it going to, when it loses 1, here comes another sodium. Sodium comes over there, sodium. Hey, sodium, I need to lose 1. The other one says I need to lose 1. Well, here you go. What happened to the other sodium? It's got 2. Not good. They both want to lose 1, so they're not going to want to share, like the diatomic elements do. Okay, so you better understand that. That's very important. Okay, you're starting with 5.5 grams of sodium fluoride, 5.5 grams of NaF. How many grams of magnesium fluoride will be produced? Ooh, here we go, yo. Here we go, yo. So what's the scenario? 5.5 grams of NaF. Bam, look at that. Perfect. 5.5 grams, there's our given. Now, to transition to the product side, we got to begin to take care of a mole calculation on this side. So I have 5.5 grams of NaF. What unit do I put down there? Gee, I wonder. Grams of NaF. How many grams? What's the molar mass? The molar mass of sodium fluoride is 41.987 grams of sodium fluoride. Okay? So, that's equivalent to 1 mole of NaF. Okay? So again, cancel, cancel. There's your mole calculation. Gee, how easy is that? So now we need to think about the actual formula, the reaction itself. We're going to transition to the products to determine how much mass will be produced. So right now I've got 2 moles. So it works out perfectly. I got to put moles down here. Moles of NF, I'm running out of room. 2. What am I analyzing? How much magnesium fluoride is produced? How many moles? 1 mole. Cancel, cancel. I need the mass. And I want to squish it a bit. Hold on, let me run it. Move it to the side a little bit. Hold on. Nothing but the best here. Here we go. All right, we got room now. So then, hold on. So then, we need moles down here to get grams. What do we put down here? Moles. 1 mole MgF2. Bam, bam, get rid of it. What do I put there? Say it! Say it at home! Sing it! Just don't say the bad word. The molar mass. You find the molar mass. The molar mass. It's a pain in the arsenic. Woo! Here we go. How many grams of MgF2? 62.301 is the molar mass. So now to determine how much this is produced, how much of that is produced, you take 5.5 grams times 62.301 divided by 41.987 times 2. Your final answer. What is it? My gosh, did I really not write it? Oh. Hold on. This is what I do for you people. Here we go. 5.5 times 62.301 equals, divided by 41.987 times 2. Perfect. 4.08 grams of MgF2. So when you start off with this, and you're reacting with this is how much you would find in the beaker. Okay. I'm sorry we don't have the actual worksheet yet. The printer didn't, for some reason, we're not printing out my stuff. So I've given you something that I hope can get you through many of these problems. Okay? Again, we'll do more practice next week, and you're going to be tested on this on the biochem exam. All right? Have fun. Have a blast. And by the way, it's pronounced stoichiometry. All right, very good. Bye.